Welcome to one more video, and in this video we are going to see what differentials are. Okay. Differentials are quantities that are related to derivatives of the functions, and they are the topic on their own, and they also have applications again related to the derivative of functions in, for example, approximations of the function. So we will later see differentials as approximations. Very good. Okay, of course, before we dive into what the differentials are, I'll just see the definition. So definition. So let f be function of real variable, and f is differentiable on some interval containing x, let's say some interval x minus epsilon, x plus epsilon. Okay, and we just let y be f of x. So a, the differential dx, so this is dx, of the independent variable x is, and I will use another color, the increment of x. So dx is just delta x. And now we want the independent variable, so b, the differential df of the function f, or since we agreed to use y instead of f of x, so we can or dy, where y equals f of x. I can put here f of x at the point, this is important, so differential is defined at the point, so let me just use at the point x is defined to be df equals dy equals the derivative of the function at the point x times the increment of x. So this is the differential of the function, or also, if you like, dependent variable. Okay, so we have the differential of, so this is independent variable, and here is the differential of dependent variable. And as I said at the beginning, they are now related to derivatives. You can see that here in the definition we have in the definition of differential of the function of x, we have the derivative. Of course, we can write df equals dy equals f prime of x delta x, okay, having that definition from the above, or just f prime of x dx. Good. Okay, so now that we know that what the differential of independent and dependent variable is, I just want to make here one comment. Here when I said differential of dx, that is the increment of x, this is meant so differential of the independent variable. So not that dx or delta x itself is independent variable. And also we have that dy, so the differential of the function is again dependent variable. So one very important thing here to be clarified is before us. So we have now the differential of y, which is f of x, okay, and we have said that's f prime times d of x. Now I would just say let us denote by capital F that differential of y. So I'll just write it here again, f equals f prime of x delta x, or f prime of x dx. And I have written here, so we have basically two parts here, and both of these, so this is function of x, because as a derivative, I'll just write here as a derivative function. Remember, we have at the beginning fixed x, but now we speak about x in general. So indeed, the first derivative is, because f is differentiable, that is the function of f as a derivative function. But this also is a function of x, because as x changes, dx changes, or delta x changes as well. Therefore, and I'll just write here, as x changes, delta x changes too. So that means that indeed this dx is a function of f. So we can say that f is a function of two not independent variables. Which variables? Well, f prime of x, so it is defined for x and dx. And we can say that's f prime of x times dx. So that means that the differential of the function f of x is a function of two variables, x and its increment, dx. So we can say dy equals actually some function x dx, and that is f prime of x times dx. This is important for several reasons, especially for the theoretical background on the differentials. If it's just easier for you, multiplication, that is also a function of, I will just say, h of xy, that is x times y. You can see that these are two variables. So the function of h, the multiplication, the usual multiplication of two real numbers is a function of two variables. Also addition, all basic operations are functions of two variables. So the usual way to think about this, or the proper way to think about the differential, is a function of two variables, x and dx. Okay. And we can also say that this function, so the domain of dy, which is fx dx, is the set of ordered pairs of the form x dx, where x is from the domain of f prime of x, okay, and dx any real number. We can even go further and say that if we consider dx as some g of x with the domain of real numbers or with the domain of some interval I interval, and I will explain why we are taking I as an interval. Actually, we can see now, because we take I to be that set where f is differentiable. So, which we can just say domain of f prime. So then we can say that dy is simply f of x g of x, and this is now it's just for those advanced learners. We can say that this is now the composite function of x and g of x. All right. So that's a theoretical background on how really the differential of a function comes in to the theory itself of analysis of a real variable. Now, if we go just formally, we remember that dy equals f prime of x dx, and we assume that dx is different from 0, so that the increment is strictly positive. So if we divide both sides by dx, we have the relation dy over dx, so the ratio of two differentials equals f prime of x. Now, there is now one important thing that we are going to discuss, and that is so important. So important thing is that the differential of the independent variable, so all right, differential of the independent x, which is dx is equal to an increment dx. So for the independent variable, as we have seen, dx is just which is increment. Increment meaning the shift of the independent variable. So if we have here x, here is x plus delta x, and delta x is then that distance or the increment. This is one-dimensional case, of course. Okay, and in general, however, so in general, dy is not equal to the increment of the dependent variable, where just for the as a reminder, that is minus f of x. Okay, so we will see now how and why this is not in general the case. So in general, we have that, I'll just write here, differential of a function. Okay, this is in general not equal to the increment. So this is increment of the function. They are in general. So in general, sometimes it can happen. Increment of the function. So we want to show that differential of a function in general is not the same as the increment of the function. That means we want to show that in general dy is not the same as delta y. And we have said that delta dy is f prime of x times dx, whereas delta y is f of x plus dx minus f of x. Here I have already started with one sketch that we are going to analyze, adding some points and more details right now. So we have function f of x, and here is x and y axis, and we have the tangent line. I will just write here tangent. Okay, where we mean, of course, tangent to the curve f of x, and here it is at the point A. Then I'm going to have several other points that we are going to introduce as we go. So let us denote here x, where we mean the point x, maybe x0, but in order to simplify the notation, I will just write here x. And then I will have here, of course, x plus delta x. Okay, so the increment here, I will just use another color. Here is the increment. I will call this point here B. Now A has coordinates, let's say x and y. Now we have also the point on the curve, which I will call point C. And C has coordinates. I'll write here C has coordinates. Let us write here also, add some. So this is y. And of course here let this be increment y plus delta y. So C has coordinates x plus delta x and y plus delta y. The length AB is the increment of x, so that's delta x. So this length here is delta x, dx or delta x, the same thing. So that's again I'll just add here. So delta x, that's the same thing. Okay, and we have here the angle theta, which I already have introduced. Wonderful. Now, what is f prime of x? That is tangent of theta. Now I will just introduce here the point D, and we will analyze this triangle here. I will purposely draw it here, not to scale of course, but it will help us to understand. So this is A, this is B, this is D, this is theta, and this is dx. Wonderful. Therefore, here in this triangle, we have f prime of x equals tangent theta. But what's that? Tangent theta is BD over AB by definition. So this is here. We have the trigonometry in. So remember, tangent of theta is opposite over adjacent, right? Therefore, if you have, let's write here again, f prime of x is tangent of theta. That's the geometric interpretation of the derivative. And that is opposite of theta over adjacent of theta, and that is opposite of theta is BD and adjacent is AB. Okay, let us just put the lengths, of course, because we are interested in the numbers, and I can say that's BD over what is the length dx. Now of course, I can multiply by dx, so I get f prime of x is, f prime of x times dx is the length of BD. I'll just write the details. I know that you already see, and you can see that these two cancel, so I have BD. So I have f prime of x times dx, the differential of x is BD. But by definition, this is dy, or the differential. So in this triangle here, this is dy. And if you go back here, this is dy. So the differential is BD, the length of BD. But what is delta y? That is the length of BC. So you can see that is this here. So I will just put here one like this, and this is delta y, and you can see that that is different from BD, which is equal to dy. So I can conclude that they are not the same. So this is an example of a function where now someone can say, okay, it is greater, it is less than dy. That's not important here. Here it is just important to see that they are not equal, and we have